Hi, this is Deepkaran Saluja. I'm a principal engineer with the secondary indexing team here at Couchbase. This video is going to be a deep dive into post-production index manageability and monitoring. We are going to talk about managing indexes in production. We'll touch base upon how to scale index service using Rebalance, node maintenance operations such as upgrade, failover, alter index placement, and changing the replica counts, adding new indexes in production, index fragmentation, and some best practices related to all these operations. And in the next section, we will discuss about how to monitor index service in production, how to do a basic index service health check, some of the important index stats, and how to use those stats to troubleshoot some common issues. So let's get started with managing indexes. So we'll start with the rebalance first. Index rebalance is typically used to scale the index service up or down by adding index service capacity or reclaiming any excess capacity. Index rebalance under the hood is really a two-step process, which is a planning stage and then the execution stage. So when the index rebalance starts, indexer will first plan to find an optimal index layout in the cluster, and it will also consider repairing any missing replicas or partitions which could have been lost due to a failover, and then it comes up with a final plan of how the indexes need to be moved. And then the execution phase begins, which coordinates the index movement while maintaining the availability of indexes at all times. And then it will monitor this execution phase and report the progress. So let's look at the details of the first phase. The index planning is about creating an index layout plan. The goal really is to place indexes for most optimal cluster resource usage. So the planner will try to find out where to place the indexes so that in terms of the usage of memory, CPU, disk, it's most optimal. And then repair any missing replicas. It'll add those to the plan. Satisfy server group constraints. If there are multiple server groups, it'll accordingly try to place them or spread them out to multiple server groups. And it will also place indexes to ensure high availability. For example, the replicas of indexes would be placed on different nodes to ensure HA. So that's the summary. It tries to find the most optimal resource usage. It uses simulating annealing method to do that. And indexer will collect the runtime stats for all indexes as an input to planning. So that would include the memory usage, data size, disk size, and also the drain rate and the scan rate of the index. So most frequently used indexes would have higher scan rate, and thus indexer would try to place them on nodes which have more resources. And for the HA, the replicas will be placed on different nodes, and it will be spread to multiple server groups, as we talked about. And any missing replica index or partitions, those would be repaired. Now coming to the execution phase, the indexes are moved around in batches. This is done to minimize the impact of rebalance on the cluster operations. For example, the existing index maintenance or the scans which might be going on. So by default, this batch size is 3, which means 3 indexes or partitions are moved at a time. And on the destination where the index is being transferred to, it will use the DCP to build the index. So it just acts like building a new index from the scratch. And while this new index build is happening on the destination, the old nodes or the old index will continue to serve scans and will keep indexing mutations. In this execution phase, it's a fully online operation. Indexes continue to serve scans. There are no scan failures, and there's no downtime. All this is managed by the system. So let's take an example of the execution in action. So let's say index 1 here has been determined to be transferred over to index node 2 as part of rebalance. This index is indexing mutations and serving scans for the query. The first step really is to transfer the index metadata over to the new node. Once the metadata transfer is done, which essentially means the definition of the index will start building on the destination node. And while this is happening, the old index is still receiving the mutations and it is still continuing to index them and serve the scans. Once the index on the destination is ready to serve scans, the query node will switch over to using that index. The important thing to note here is that on the old index node, any scan which was in progress will still finish before any cleanup happens. And that ensures that there are no scan failures during rebalance. Another important property of rebalance is that any failure during rebalance doesn't cause index data or availability loss. Any index which have successfully moved to their new destinations, they will remain there, and any in-flight index movements will be discarded. So which means that if the index rebalance fails at 90%, whatever indexes had moved, those are considered successful, and that work itself is not discarded. Only the in-flight index movements are discarded. The rest of the work is retained. And the failed rebalance can be rerun from the UI. The subsequent rebalance will work incrementally to achieve balanced resource utilization. Now let's look at some of the examples of what happens when some of the common cluster operations are performed in an index cluster. So this one here is an example of adding a new index node. So here there's a cluster with 2 index nodes. Both have a couple of indexes, and a new node is being brought in the cluster. And let's say if the rebalance is done, then the third node joins the cluster. However, there is yet to be any index placed on it. So a non-partition index is not moved when a new index node is added. This is done to minimize the cost of index movement because moving an index is equivalent to creating the index from scratch. But in the future versions, there will be option to optimally place indexes on node addition as well, so that there's no manual work required for administrator to move indexes around. As of now, alter index can be used to place indexes on new node. So for example, after this node 3 is part of the cluster, some of the indexes can be moved using alter index to the new node. And here we see in this alter index, the index name can be specified, which needs to be moved. The action is moved, and then the destination can be specified. The next example is of a failover, or rather how an add new index node works in case of a failover node. So let's say there are two nodes in the cluster, and one of the node fails over and goes bad. It can't be recovered. In such a case, if a new node is brought into the cluster and rebalanced in, after the rebalance, the system will automatically restore the replicas, and whatever the lost indexes were there on the failed over node, they will automatically get repaired on this new node. But it is essential for all indexes to be defined with replica for this automatic repair to work. So any missing or lost index replica will be repaired and placed on a new node whenever a new index node is brought into the cluster. Let's look at how this works for a partitioned index. So in this case, again, there are two index nodes. Now the difference is the indexes are now partition indexes and have their partition spread across these two index nodes. And a new node is brought into the cluster. Here we see that automatically the system moved the partitions of the index to the new node. So partitions of a partition index get moved when a new index node is added to optimize the resource utilization on all nodes. This is different from a non-partitioned index. For a partitioned index, the system will automatically balance out and spread the partitions whenever a new index node is added. So this is a good feature which can be used for ease of manageability. Anytime the system is required to automatically manage the index placement with partition index, that can be done. Now, next, let's talk about swap rebalance. In this cluster, again, there are two index nodes. Both have indexes, and a third node is brought into the cluster. So swap rebalance actually means that the number of nodes moving out of the cluster is same as the number of nodes moving into the cluster. So in this case, the index node 2 would move out, and index node 3 will replace the index node 2. So here we see that the incoming node, index node 3, has got both the indexes which were initially hosted by index node 2. So swap rebalance is recognized as a special case by the indexer system, and indexes are moved one-to-one to incoming node from the outgoing node. And this happens for both partition as well as non-partition indexes. Now let's look at what happens when an index node is removed. So in this example, there are 3 index service nodes, and all of the nodes have indexes or their replicas, and index node 3 is going to be moved out. Here we can see that the indexes that were hosted by index node 3 they have been moved to index node 1 and 2. So from the initial configuration of 2 indexes being hosted on each node, now there are 3 indexes on each node, and all the indexes and the replicas are available. This functionality is also same irrespective of partitioned or non-partitioned indexes. So whenever a node is moving out, the system will automatically make sure that from the outgoing node, the indexes and partitions are moved to the remaining nodes in the cluster. Now let's look at another example of remove index node. Now again, there are 2 index nodes and there are 3 indexes and with 1 replica each. So total 6 indexes. Now if this index node 2 is moved out of the cluster, now the replicas will be lost because there is only 1 index node in the cluster and there are 3 indexes and 3 replicas. So replicas will not be placed on the same index node as the original index. So this is something important to note. So some replicas may be lost if there are not enough nodes in the cluster. However, the important point to note is lost replica will be automatically repaired when more nodes are added again. So in this case, if another node was added again, it will again repair these lost replicas and the system would look similar to this. Now let's look at node failover and recovery. For example, let's take 2 index nodes and one of them fails over and is not recoverable. Actually, this is an example of recovery. So in this case, this node is able to recover. So once after failover, the administrator recovers the node. The indexes on the node are automatically recovered from the disk snapshots. And this is a very fast process because all the data is on the disk. It just needs to recover it and catch up with the delta mutations remaining from the data service. So this applies equally to both memory optimized and GSI indexes. So on recovery, no index rebuild is required. The recovery is fast. It just recovers from the disk snapshots and then index the delta mutations from the data service. So recovery is always a preferred option whenever there is an option to do that. Now let's look at node upgrade and maintenance. So we recommend to use the same strategy of failover to perform any node upgrade of maintenance or maintenance operation, as that's a very fast process as compared to rebalancing out the node, patching it, and then rebalancing it in. So the idea is that the node is failed over, it is upgraded or patched or any other maintenance operation, and then just recover the node. Now on recovery, the node will come up and catch up to the data service very fast. So that's a quick way to do any node maintenance. Now it is important to make sure that all index have replicas if this strategy is opted, so that all the scans and all the index maintenance operations can continue on the replica. So indexer will make sure that the traffic is automatically switched over to the replicas. And another important thing to note is that the replica should be able to sustain production workload, or it's better to choose a quiet period to do any maintenance operation. So this can be much, much faster as compared to swap rebalance. Another important aspect of manageability is alter index. Alter index allows an administrator to do many things. The most common operations are changing the index placement. So for example, like we discussed before, that if an index is required to be moved from one node to the other, then alter index can be used. This can move an index or its replicas to different destinations using a single alter index command. Another important usage is to increase or decrease the replica count. So for example, if an index was originally created with one replica and now the requirement is to add another replica for a particular index, then this replica count can be used. And for example, if this index had one replica and then if replica count is specified as 3, the system will automatically increase the number of replicas for this index to 3. Also, alter index can be used to drop an existing replica. So for example, the drop index by itself will drop all the replicas of an index. However, using this method of drop replica, a replica ID can be specified, which will only drop the particular replica for this replica ID. All the other replicas will continue to function as it is. This can be used if one replica gets corrupted or needs to be dropped for any other reason. The system will automatically repair the dropped replica on next rebalance. Now let's talk about creating new index in a production cluster, which is often a requirement. So while creating a new index in a production cluster, it can be, the placement can be system managed or user chosen. If a with nodes clause is specified in the create index, the system will honor those nodes and place the index there. Or if no with nodes is specified, the system will try to find the most optimal placement on its own. Some of the important things to note about new index creation is it needs a good amount of CPU, memory, disk IO to build an index, because to build an index, the whole bucket needs to be scanned and all the documents need to be evaluated, and accordingly the index build will happen. So there needs to be enough spare resources on the system. And also the new index creation is going to evict out the already existing indexes from the cache. So if there is not enough memory or there is a memory pressure, the new index getting created is going to cause evictions, and this could disrupt the working set of the index, and it could lead to slower scans for the existing indexes when the new index is getting built. So this is something to be aware of, and accordingly, index should be created on those nodes which have more resources, or the administrator should make sure that the system is not already too much overloaded before creating indexes. Index fragmentation. So for standard GSI, in the EE Enterprise Edition, the system automatically manages index fragmentation at 30%. There's no user action required. So whenever a system will see that the fragmentation is beyond 30%, it will automatically try to run its compaction and get it below this threshold. For memory optimized indexes, the fragmentation does not happen because on the disk, the snapshots are full index copy and are only used for recovery. So there is nothing to be concerned as as far as fragmentation goes. On the community edition, it is recommended to use the default mode of circular compaction. And this allows the storage system to reuse the stale entries on the disk, and it's a much more optimal way for the storage engine to work. And by default, that's the setting which is defaulted to circular mode. And if the other option is to trigger fragmentation based on a specified trigger in terms of percentage of fragmentation, although the recommendation is to use the circular mode so that the reuse can happen and it's much more optimal. Moving on to the next section about monitoring indexes. In order to do an index service health check, a couple of things are important. First one is to check if the index service nodes in the cluster are healthy, and then the indexes are online. This information is available in the Couchbase admin console. Under the servers section, all the index service nodes, this metric is displayed. The status is marked as green for all the healthy nodes. If any node is not running or not reachable in the cluster, this would turn as red. Similarly, for each index, the status is shown in the admin console. A green index would mean the index is available and the indexer process on the node hosting this index is running. If there is a problem, the admin console would show something like orange here or a red to indicate that there is a problem with the process. Now, in addition to this, when the node is healthy and the index itself is online, another important aspect to look at is something called as pending mutations. Most problems in the indexing processing pipeline would result in mutations pending to be indexed. So let's look at it in a little bit more detail. A quick look at the index architecture. So here is an index service node, and which is hosting a few indexes. And here's the data service node. Now, global secondary indexes are asynchronously maintained, which means the data changes are streamed from data service to the index service. And pending mutations means that there is a problem in this pipeline from where mutations are streaming from data service to the index service, or the mutations are coming into the index service, but index service is not able to either process those or keep up. Any of these problems in the whole pipeline, right from mutations starting from the data service to getting indexed in the storage, would result in these mutations being pending to be indexed. Now, in order to identify these mutations remaining or pending, the admin console has this number in both the summary stats as well as in the mini graphs. And if this number is high, it means there is some problem in the processing. And These statistics are also available over the REST API, and these are available at a per index, per partition, per node level. For this particular statistic in question, the high index mutations remaining, let's take a look at that one. So the mutations remaining on the UI or admin console that we just saw is actually a sum of two statistics, the numdocs queued and numdocs pending. Let's look at what these mean. Numdocs queued represents the number of documents queued up within indexer waiting to be processed. So if we look back at this architecture diagram, it indicates that the mutations have reached the index service node, but the index service node is not able to process those mutations. So which means that the problem is most likely within the index service. On the other hand, if the numdocs queued is 0 or very low, it means index node is able to keep up with the mutation traffic. And still, if the mutations remaining is high, which means the numdocs pending is high, it means that the problem is on the producer side. Is it's either with the projector, which is another process which runs on the data service node and forwards the mutations to indexer, or even before that. So in order to check that, the projector or the network latency then needs to be looked at further. We'll go into the detail of this. Now, let's look at the first case in a little bit more detail, the numdocs queued. So we see that 100K documents are queued up, and it's the drain rate is low. Or the drain rate is 0. The mutations remaining are not going down. And now, if those are queued up at indexer, then the first thing we need to check is the index node resource usage in terms of its memory resident, CPU, disk IO, and then identify where the bottleneck is. So let's look at the index memory resident and how that plays a part. So index memory resident really represents the percentage of items for an index available in the memory or the cache. And it is recommended to keep all indexes at 20% resident. A lower index memory leads to increase in the disk IO requirement for index operations. And it results in lower indexing throughput, which is the drain rate, or the higher scan latency. Memory optimized indexes, they are always 100% resident. Now, if the memory is determined to be low, then that can be changed from the UI settings. So in order to check and verify that what is the resident percent of an index, then for each index on the admin console, in the summary stats, the resident percent is displayed. And also on the stat rest endpoint, there is a stat resident percent per index which can be used. And if the index quota needs to be increased, it is under the settings. The quota can be changed. And, this increased allocation will improve the index throughput and latency. The next factor to look at is indexer CPU. So by default, indexer uses all the cores available on a node. Indexer has a highly concurrent design and can scale to use high number of CPU cores. to achieve high throughput for both index build as well as scans. Um, and if the CPU gets saturated, it will lead to slow index builds and slow scans. This can also be changed by a UI setting. Uh, in terms of monitoring, again, the CPU is uh, displayed on the admin console, or it can be monitored using any other external tool. And the console also gives an ability to view the CPU usage over a period of time, let's say a day or a week, to see how the CPU is getting utilized. And if the CPU allocation needs to be changed, again, it can be changed under the cluster settings. Coming on to the disk. From the perspective of standard GSI, the disk IO is required for the index updates, for the scans to fetch non-resident pages, for housekeeping operations like compaction, MVCC purge. So it is recommended to use a standard SSD to achieve a good throughput. And a related aspect here is that more memory can help alleviate disk IO requirement, as less pages need to be fetched in memory for index updates as well as scans. So anytime a disk IO is seen to be saturated, uh, it is a good idea to give more memory, and that can help alleviate that bottleneck. In terms of memory optimized indexes, um, those only store the index snapshot on disk for recovery every 10 minutes. So that would lead to disk IO usage, but it is generally not a bottleneck for performance. An important optimization that has gone in the 6.6 product release is the addition of Bloom filter to help optimize the incremental index build or the index maintenance. This reduces the disk IO requirement for looking up old index values. This is specific to standard GSI, and this is helpful in low memory resident cases because generally in those cases, disk IO is the bottleneck. And it can help to increase the indexing throughput at the expense of a little bit more memory to maintain the Bloom filter itself. So that's a useful optimization to look at. Another factor that plays a role in the indexing throughput or which can saturate the disk IO as well is the size of the index keys. It is recommended to keep index keys under 1 KB, and larger index keys increase the disk IO, and it causes more memory usage as well. Especially we have seen that covering indexes with large arrays that can lead to suboptimal performance. So that's another area to look at when doing a health check for the index service. This metric is again available on the admin console as a mini graph per index. So this was about high numdocs queued, or high number of items queued within the index service. Now, if that number is low or zero, then the other aspect needs to be looked at, which is on the data service where the projector process is running. So the projector process, it runs on each data service, and it extracts the indexed field from each document and forward to the index service. And the key thing to note here is that projector is a CPU intensive process because it needs to parse the document, extract the field, and keep forwarding it to the index service. So by default, the projector CPU allocation is capped at 25% of the available cores on the data service. And if this is saturated, then it can lead to high numdocs pending, where indexer is not getting enough to index. And this can be increased by via setting change, which is this projector max CPU percent. So the main factors which lead to high CPU usage for projector are, the number of indexes, the size of the document, the complexity of indexed expressions. So if the cluster has really high number of indexes, and then this is something to be watched out for, that if projector is already saturating its CPU, then that giving more CPU allocation to projector can help alleviate that bottleneck. For example, here is a snapshot of a system where projector allocated 4 core for itself, as the nodes had 16 cores. And we can see that projector is capped. It's able to utilize and saturate all the 4 cores. So in such cases, projector would generally become the bottleneck in this processing pipeline, and it's a good idea to give more CPU to the projector. Another useful stat which the index service records is called projector latency. This is the latency observed with respect to each data node. And this latency can be monitored to track and identify any bottlenecks in the processing pipeline. So this number can be thought of as an end-to-end processing latency number. And this can be monitored, and anytime this number is going higher, it means things are slowing down, and this is a good number to monitor. The next, we'll look at how to debug a slow scan. So there are multiple factors which can slow down a scan. The first one is CPU saturation. So for example, there are a lot of full index scans or aggregate pushdowns or too many requests. All these can lead to a CPU saturation on the indexer side. And again, these, if CPU is saturated or not, it can be monitored from either the admin console or an outside monitoring system. And if slow scans are observed, or scans are timing out, CPU is saturated, then either the query needs to be optimized, or if the query is already optimal, it's just that the load is high, then the indexes can be spread to more nodes, or an additional replica can be added to alleviate if a particular index is becoming a hotspot, or an index itself can be partitioned, because index partitions are processed in parallel. So that allows more better latency for the scans. Another case for a slow scan can be if consistent scans are being used, which are also called the request plus consistency mode. Now, important thing to note is that index needs to catch up with the absolute latest mutations in the data service before it can answer a consistent scan. And anytime there is any pending documents in the pipeline or any slowdown, the consistent scans would see higher latency. So again, if consistent scans are slow, the same stat for pending mutations can be checked and seen that if where the bottleneck for the processing is. Another case for a slow scan can be if the memory resident of an index is low. Now, that would mean that most of the items for the index that need to be scanned are not available in the cache, and it needs more disk IO to answer such requests. In such cases, allocating more memory can help. And in order to identify that such is the case, there are stats to monitor the cache miss ratio or cache percent. And if the index in question is having a high cache miss ratio, a low cache hit percent, then it means that allocating more memory is going to help. These stats are available in the admin console as well, the index cache miss ratio, and it can be looked up from there. Index ROI, that's another topic where sometimes the administrators need to find out for a particular index what kind of resources are being consumed versus how many scans are being answered. So there are some useful stats which can be used to answer this question. For example, the resource usage of an index can be seen by the data size, disk size, memory used, and how many scans it's answering can be checked using the stat, the num requests. There is another important stat which tells when was the last time an index was used. So over a period of time, there can be indexes which are no more being used and they just stay in the system. Using this stat, such indexes can be identified and cleaned up. Again, these stats, the index request rate and the last scanned, they are on the admin console with each index. And also the resource related stats such as the data size, the disk size, the memory used, and those are available on the admin console as well. So these are some of the important stats which give useful information. And thanks for joining me in this session, and have a good day.